Welcome back everyone. In this lecture, we will actually continue with the sl2 representation theory and observe some basic facts about sl2 representations. So, let us begin with finite dimensional representation of sl2. Let us call it capital V being a given finite dimensional representation of sl2. So, then using Weil's complete reducibility, we know that V can be written as a direct sum of irreducible finite dimensional representations of sl2. So, since direct sum actually commutes, V direct sum W is isomorphic to W direct sum V. So, we can arrange this V as V M1, let us say K1 copies of M1 appears and so on, and VMR KR copies of VMR appears in V as summands. Okay. So, without loss of generality, because all these direct sum commutes, we can assume that M1 is strictly greater than M2, strictly greater than M3 and so on. Okay. So, this basic assumption we can actually make. So, now what we are interested in understanding, so we want to understand that when given irreducible module V of M occurs as a summand inside capital V. So, that is the first question. Okay. So, question 1. So, given V of M when it occurs in V as a summand. So, is there any easy combinatorial way to determine this? So, that is the basic question. So, give characterization of multiplicity of V of M inside capital V. So, that is the second question. Okay, more or less both are relevant. So, give explicit formula for computing multiplicity of V of M, that means how many times it occurs inside the direct sum. So, this K1 etc. Kr, they are called multiplicities of this respective V of M1 etc. V of Mr. So, give explicit formula for computing multiplicity of V of M in capital V, of course, in terms of capital V. So, this is something that we would like to do it in this class. Okay, so let us make some observations about given general representation with respect to this given decomposition of V into direct sum of irreducible modules of sl2. So, first thing to notice, okay, let me state it as a proportion. So, all these are immediate observations from two important facts that we proved about sl2. One is we have the explicit classification of all irreducible finite dimensional modules of sl2. So, that is given by this V of M, where M is running over all non-negative integers, and we have complete reducibility of any finite dimensional representations of sl2. So, using this we want to conclude few stuff. Okay, let us first recall what we know about given finite dimensional irreducible representation of sl2. So, let us say M is a given non-negative integer. So, then we have this irreducible module associated with this M, we call it Vm. So, we know that it has a very nice this weight string basis. Okay. So, there is this basis which we can call it as a string basis because it has a nice property. So, let us call it V0, V1 etc. Vm, whose h weights will be given by m, m minus 2 and so on up to minus m. So, basically all the h weights are, they are unbroken chain starting from m to ending with minus m. So, whose difference all will be like successive difference will be just 2. So, in particularly all these weights have same parity as m. Okay. So, note that all weights have same parity as the highest weight, that is m, as the highest weight, which is m. Okay. So, now using this and whilst complete reducibility, it is immediate that, so let me make the first statement. So, this is indeed observations, but let us state it as a proportion. So, you have the action of H. So, H acts diagonizably on capital V, because V can be written as direct sum of irreducible representation. On irreducible representation, H acts diagonalizably. So, one can immediately conclude this from Weil's theorem. But anyway, we proved this in some different ways. Okay. So, this is the first important observation. Not only that it acts diagonalizably, and all the eigenvalues, okay, all eigenvalues or the weights, okay, the H eigenvalues are called weights of this representation. So, they are all integers. So, that is an important observation. This is A and this is B. And if we take this other operator x and y, they act nilpotently on capital V. Now, you can explicitly compute what will be the nilpotency on the irreducible module. Using that and using this explicit multiplicities k1 etc. kr, you will be able to compute nilpotency of these operators on any given capital V. Okay. So, now not only this, we also have this very important property of the weight multiplicities. So, that is the symmetric property. So, if we call Vk, so let us write V as direct sum of Vk, where k runs over Z. So, this is just the weight space decomposition. That means each Vk, so these are all weight spaces corresponding to the action of H. Okay. So, more explicitly Vk is given by those vector in capital V such that Hv is given by Kv for all, okay, Kv. So, we know that this is indeed called eigenspace or the weight space of H. The dimension of this Vk, they are called weight multiplicities or the weights. Multiplicity of the weight space Vk, which is also called weight, of course, weight of Vk. So, now one can easily observe that dimension of Vk is same as dimension of V minus k, and this is true for all k integer. So, why this is true? Because this is true for irreducible module. So, if we take all weight spaces of this irreducible module Vm, we observe that all of them are actually one dimensional, and whenever some weight k appears in Vm, then the minus k also appears and the dimension of that is also 1. So, because of that you can immediately conclude the kth weight space of Vk has same dimension as minus kth weight space of V. So, now we can also actually try to compare the weight multiplicities. So, it is immediate that if we take these weight multiplicities, let us only focus on the even and odd parts separately. Okay. So, then you can easily see that the dimension of V naught will be greater than or equal to dimension of V 2, which is greater than or equal to dimension of V 4 and so on. Similarly, if we take the dimension of V 1, which will be greater than or equal to dimension of V 3 and so on. And this is again very clear from the Wild's complete reducibility. So, let us draw some picture, then that actually will give you proof of this immediately. So, let us say that we have decomposed V into V of m1 direct sum k1 times and so on, direct sum V of mr direct sum kr times. So, as before, without loss of generality, we are going to assume that m1 is greater than etc. greater than mr. They are all distinct and strictly decreasing. So, now if we take the, for example, the very first copy of this V m1 direct sum k1. So, what we get? So, we get some picture like this. So, all this Vm, so they just appear here. Okay. So, this is just a copy of Vm1 and so on copy of Vm1, and the number of times it appears is k1, k1 times it appears, and you have the weight spaces that actually just get decomposed. Okay. So, here the top weight m1 appears, and here the lowest weight minus m1 appears, and the second level you have m1 minus 2, and here as well you have m1 and m1 minus 2 and so on, and then you have minus m1 here. Okay. So, this is how this entire copies of Vm1 appears inside capital V. Okay. Just a pictorial interpretation. So, now if we go to the second level, so let us use different color. So, we go to let us say second level Vm2 direct sum k2. Okay. So, then Vm2 may appear somewhere, and then it may actually give you something like this. Okay. So, you have Vm2 copies of Vm2, and then how many times it appears? It appears k2 times, and then here the top weight will be m2, here m2, and then the bottom last weight will be minus m2 and minus m2. So, now like this you have all these modules, and then finally you end up getting something like this Vmr. So, this will be Vmr, Vmr and so on. So, this will be Mr and then Mr and then minus Mr minus Mr. So, this is how the combinatorial picture actually looks like. Okay. So, this is how capital V is decomposed as direct sum of irreducible modules. But then this is actually kind of working backward. If we know this decomposition, now we can get all information about capital V. For example, if we fix some weight A and then ask, so what will be the actually dimension of that weight space VA. So, let us try to compute it using this diagram. So, you can see that, so this weight may occur somewhere here. Okay. So, this could be the weight that corresponds to A. So, then if I take this particular stripe which corresponds to the weight A, so then it may occur in many different irreducible summands. Okay. If we put them together, then we get the dimension of VA. Okay. So, it can appear inside the first component, it may appear in the second component and so on. So, now if I fix one of those things, let us say one square like this, where this A appears. Okay. So, that is going to contribute that particular V mi, that summand is going to contribute one dimension towards the dimension of V A. So, that means what will be the dimension of V A? So, if you just think about it, it is very clear that the dimension of V A, where A is just one of the H weight, then that is going to be exactly equal to. So, you collect all possible uh, these MIs. Okay. So, that is nothing but the irreducible module that appears in capital V. So, what is exactly that? So, this is a direct summand. Okay. So, this is going to be. So, to collect this V A, we need to look at the particular irreducible copy. Okay. So, that means if this A appears there, then we have this obvious relations. So, let us say A appears in V m. So, then that immediately gives that this m must be greater than or equal to mod A, because m is the highest weight. So, if A appears or minus A also appears inside V m, that means both A and minus A should be smaller than m. So, that is the first condition. And then as we observed, all the weights that occur inside given irreducible module, they all have same parity as m. So, if we take any weight in that appears inside this irreducible module V m, that should have same parity as m. So, that tells you that if we take this A, if it appears in V m, then that's A and m must have same parity. So, m and A must have same parity. Okay. So, in other words, one can say that m minus A is even. So, this is equivalent to saying m minus A is even. So, now we can actually easily count what will be the dimension of V A, because each one that is that each m that satisfies this property that comes from this collection is going to give you one dimension contribution to V A. So, that means this dimension of V A is going to be the number of direct summands that are isomorphic to V m. Okay, isomorphic to V m, where this m should have satisfy this property, m is greater than or equal to mod A and m minus A must be even. Okay. If these two properties are satisfied, then that contributes one dimension to V A. So, you count all of them, then that is will be the dimension of this V A. Okay. So, this is indeed very immediate important observation that we can make. So, now using this you can easily conclude that these inequalities are satisfied. Okay. So, if we take for example dimension of V 0, so that is going to be the number of direct summands isomorphic to V m, where m greater than or equal to 0, that is obviously satisfied, but m minus A being even is just saying that m is even number. Okay. Now, if you go to dimension of V 2, then that puts the condition that m must be greater than or equal to 2 and m minus 2 is even, that is same as saying m is even. So, every time you can see that the numbers of that such m's going down. Okay. So, that actually tells you that the dimension of V 0 is greater than or equal to dimension of V 2 and so on. Similarly, you can conclude that dimension of V 1 greater than or equal to dimension of V 3 and so on. So, now let us have a closer look at this number of summands that we are actually getting. So, if we take this K1 etc. Kr, that are also we are interested in actually computing. Okay. So, let us actually count this number of summands that are isomorphic to Vm. So, this is exactly the multiplicity of Vm inside capital V. So, the word multiplicity is overused. It is used for the dimension of the weight space. It is also used for the number of times Vm occur inside capital V and so on. Okay. So, you should not get confused. So, now what is this exactly? So, now if you go with this formula, you can easily see that the dimension of Vm indeed actually captures something very closer to that number. Okay. So, let us look at the dimension Vm. So, the dimension Vm, so what it is? It is the number of direct summands isomorphic to Vm. So, where m greater than or equal to that mod A is already satisfied. Okay. So, let us say number of V of m dash that appears in capital V, where this m dash is actually greater than or equal to m and m dash minus m is even. Okay. So, this is what you are getting for the dimension of Vm. And similarly, if you look at dimension of Vm plus 2, then again you are going to get very similar formula. Okay. So, now using these formulas, or maybe like one can use the diagram to say very explicitly what is happening. Okay. So, let us say I am interested in actually counting this K1. Okay. How many times this V of m1 that occurs inside capital V. So, that if you think about it, so that is exactly captured from the dimension of this V m1. Okay. So, if we take this particular space, so this is what that actually captures the number of times this V of m1 that appears inside capital V. Okay. This is the dimension of V m1. So, now if we go to actually V of m2, okay. So, how one can actually calculate this K2. So, let us see. If we are interested in this calculating K2, then what we need to do, we need to actually first see how. So, we are interested in calculating everything in terms of capital V. So, we have to say everything in terms of actually weight spaces of capital V. So, that will be sufficient. So, now let us look at this particular stripe where m2 actually occurs as the weight. Okay. So, this is going to be Vm2. So, that is the weight space of capital V corresponding to the weight m2. Now, if we take this stripe, this particular stripe, so then you can see that this K2 number of copies of Vm2 appears somewhere here. So, this is actually is what contributes to the copies of actually Vm2, but there are some extra dimensions that are actually coming from this. So, some part of this is actually giving something extra. So, how one can actually subtract that extra from this entire thing, so that we can get this. So, this is just a inclusion exclusion. You can see that to get the number of times that K2, so let me write the formula here. So, this K2 is exactly equal to, so you look at this entire space. So, that is the dimension of Vm2. Okay. So, this is the whole space. So, that is actually giving you the dimension of weight space of capital V associated with M2. So, now if I want to subtract this part, So, then that is exactly the number of times k1 that appears. So, that for example can be captured by just subtracting this V m2 and then V m2 plus 2. So, you can go just m2 plus 2, which is just a little higher weight that appears here. So, this is the weight m2, then you go to the weight m2 plus 2 and the dimension of that m2 plus 2 that cannot come from something irreducible modules that is uh, smaller than m2. Okay. So, that means, so that weight space contribution cannot be obtained from the smaller things. So, it has to come from something bigger. So, that part if you just subtract from entire thing, then you will be exactly getting the number of irreducible modules that that number k2, that the multiplicity of that inside capital V. Okay. And this thing works for all other things. So, from that you can easily see that the number of summands that are isomorphic to Vm. So, that is going to be exactly, you take the total multiplicity of m inside capital V. So, which is what somewhat partially contributes to the weight spaces corresponding to this top weight spaces corresponding to Vm. Okay. From that, if you just delete which cannot be obtained from the lower irreducible modules. So, the part of the weight space which cannot be obtained from the lower irreducible modules, then you get exactly the number of summands that are isomorphic to Vm. Okay. So, this is again very easy formula that one can actually prove using the observation. So, now it is also immediate that if you are interested in counting total number of summands, okay. So, the number of total number of summands that appears inside your module capital V. So, that means this is the k1 plus etcetera plus kr. So, what is this going to be? So, this is going to be exactly the dimension of V0 plus the dimension of V1. So, that is because if I take one irreducible module Vm, okay, let's take it here. So, if this is Vm, so now depending upon the parity of m, so either this particular irreducible summand contribute to the weight space corresponding to 0 or 1. Suppose m is even, then there will be one weight space corresponding to 0 inside this V of m. So, that is going to contribute to capital V. If m is odd, then there is a one dimensional weight space corresponding to the weight 1, that is going to contribute to the weight space of capital V, which corresponds to 1. So, that means each summand Vm contributes to either to the 0th weight space or the 1th weight space, because they are mutually disjoint. So, their sum is going to give you exactly the total number of summands that we are interested in. So, if you are interested in for example, proving some module is irreducible, so you can actually try to compute this number dimension V naught plus dimension Vn. If you can say that that number is just 1, that proves that the given module is irreducible. So, this is something like that we are getting it for free. So, moreover, we can also actually put all these things together and then say something more about the multiplicities. So, this is from the combinatorial viewpoint, okay, from combinatorial viewpoint, we can say that all these numbers that actually occur here, they are all having this important property of the So, from the combinatorics point of view, we can also see that if given finite dimensional representation capital V, and then if we take the multiplicities of that capital V, then the following sequences. So, let us say this dimension Vk where k is odd, and the dimension Vk where k is even. So, these two sequences, the sequences. So, these are actually satisfy these following properties. So, both of them are unimodal and also symmetric, and it is symmetric about the origin 0. Okay. So, we already proved that dimension of Vk is same as dimension of V minus k. So, that takes care of this symmetric about origin. And why this is unimodal? So, unimodal is exactly translates to these inequalities. So, basically you have actually both positive and negative weights. So, you can see that. So, this first condition indeed tells you that. So, dimension V naught is actually bigger than dimension V2 and as well as bigger than dimension V minus 2. And similarly, you can go down. So, the dimension V2 is bigger than dimension V4, which is again bigger than dimension V minus 2, which is bigger than minus 4. So, basically one can write it as this one inequality, one sequence of inequalities, but if you just use this symmetric property, you can see that it is indeed unimodal. So, yes, positive real number sequence or any sequence of real number, it is called unimodal if it goes up to some stage and then comes down from that stage. Okay. So, let me make a very precise definition. Yes, a real sequence, let us say A1 etc. An is said to be unimodal if there exists k, of course, between 1 to n such that, so up to that k it increases and then after that it starts decreasing. Okay. So, if you have actually a sequence satisfying this property, then you call that sequence as unimodal. So, if the sequence is symmetric about 0, then of course, you have like you have plotted. So, this is actually origin, you plot the sequence here and here, and then obviously it's symmetric about origin means, so the numbers a k is same as a n minus k. Okay. And now symmetric about origin actually implies unimodal. Okay, that is obvious. So, basically the second statement that we have about these inequalities is translated in combinatorics as unimodal. So, in the next class, I will actually give one immediate application of this SL2 representation theory in combinatorics and demonstrate the power of this theory. Okay. I will stop here, we will meet in the next class.